if you'll remember, Unit 3 was work and energy. You're going to see significant similarities between momentum and energy and significant similarities between impulse and work. They share a lot of the same ideas, and they're not intended to be studied separately. They're intended to be studied together. So the things that were deficient when it came to energy, stuff like how long it takes for something to happen or the direction that something happens, they are part of momentum and impulse. And the things that momentum and impulse are deficient about tend to be part of work and energy. The idea is that these two topics work together to help predict things that happen in the future. But we're going to focus on momentum and impulse with the knowledge that we've studied work and energy. So both of them will be used. So the homework you're going to have is going to have a lot of work and energy stuff in it because we are adding to that, not studying something that is separate from that. Now, if I've got, 15 physics books over there. If you take those 15 physics books, half of them would teach momentum and impulse first and work and energy second. They can be taught in either direction. So I'm teaching in the order that I'm supposed to for AP, but generally momentum and impulse and work and energy are a combined topic. You need both to understand what's actually happening in nature. But we're going to focus for a few minutes on momentum. The word impulse means change in momentum. So let's first define momentum. Momentum is just another quantity in physics. And I know you're going to love this, but momentum is given the letter lowercase p, because as you probably imagine, m didn't make sense because m was already used for something else. So they just went up a couple of letters, and we are going to use p. And obviously, this is mass, and this is velocity. If you'll remember from our first semester, mass is a measure of inertia, so this is talking about inertial mass. So this whole thing is a measure of an object's inertia due to motion. Now, we talked about inertia. We talked about it first semester. If you don't have a definition in front of you because it was so long ago, inertia is an object's resistance to change in motion. That's a definition of inertia. It's worth rewriting again. Inertia is an object's resistance to changes in motion. Remember, heavy things were hard to move, light things are easy to move. That's inertia. We're going to complicate inertia a little bit now, because you can increase something's inertia by making it move. Things that are moving also have inertia. The more they move, the more difficult they are to change. Again, the more they move, the more difficult they are to change. So this is a measure of how difficult it is to change an object's motion. That's what momentum is. Something with a lot of momentum will be difficult to change its motion. So if a bus is traveling towards me at 5 miles an hour and a bicycle is traveling towards me at 5 miles an hour, and I'm going to have to be hit by one of them, which one is probably going to be better to be hit by? Sure, the bicycle. I'm going to assume it has less momentum than the bus, and therefore it'll be easier for me to change it. Now, don't get me wrong, there are plenty of things that have lots of inertia that aren't very big. Can you name some ideas here? Yeah, it's probably the most easy one to come up with, right? A bullet itself is only a couple of grams, but put 300 meters per second behind it, it's suddenly very difficult to change. So when we talk about momentum, momentum isn't just about how big an object is. It's a combination of the object's mass and velocity, and that creates a new measurement, momentum. Momentum is a vector. It has direction. That's going to become incredibly important here in a few minutes. So momentum gets a little vector bar, and the direction of momentum is the velocity. Got all those definitions in there now? Don't need to repeat any of that? Now, let's get back to what we were talking about. What we were talking about just a minute ago is actually called impulse. Impulse has two parts. It has the cause and the effect. The effect of impulse is the object's change in momentum. Applying an impulse to an object will change its momentum. So impulse is the change in momentum of an object. That is the effect. That is the outcome of applying an impulse. And I can write that really simple like, or I can write it more complicated. And if the object's mass doesn't change, I can write it even more complicated. Now, I'm being careful. That's if, you should put in there, if the mass doesn't change. There are plenty of examples where that's not true. A rocket, bless you, a rocket's mass is changing, so its impulse is more complicated. But for like basic things like a ball or the egg or a boxer's fist, the mass doesn't change while its momentum is changing. Now, I want you to keep in mind, I talked about a couple of examples, and I talked about them purposefully. So let me draw one of them so that we have an example here from which to work. Okay. You all heard that too, right? Okay, so wine glass, one above carpet, one above tile. And we'll say this is a meter above the ground in both cases. And let's say they are identical glasses, so they both have the same mass. We just talked about this, and I'm going to fool you, and it wasn't intentional, but you'll be easily fooled. When the glass on the right hits the ground, will it be traveling faster or slower or the same as when the glass on the left hits the ground? Why? Right. I would say because they're both falling from the same height. Is that reasonable? mgh equals 1/2 mv squared. They both fall from the same height, so both traveling the same speed when they hit the ground. So they both start with the same amount of momentum. Right? And when I say start, what I mean is the instant they strike the ground, that's the start of this conversation. So there's the instant they strike the ground, that's the start of our conversation. So when both of them hit the ground, they both have the same momentum. They're the same mass, and they're traveling at the same velocity. Does that make sense? Now, advance a few seconds. Well, no, I don't think it takes a few seconds for this to come to rest. Probably this would be measured in milliseconds. So right when it hit the ground, they both have the same initial momentum because they have the same initial velocity. Then there's just pieces of glass here, and there's a glass here. What's the momentum after they hit the ground? Not trying to trick you. 0, sure. 0 momentum here, 0 momentum here. which glass experienced the larger momentum change? The glass on the left or the glass on the right? I'm trying to trick you. The change in momentum on the right is 0 minus the final momentum, and the change in momentum on the left is 0 minus the initial momentum. And the change in momentum on the left is 0 minus the initial momentum. They're the same. They both experience the same change in momentum. That's the first thing I want to say to you. Change in momentum is merely about how much something changed. Both of these had the same change in momentum. They both started at the same velocity and ended at the same velocity. So they had the same change in momentum. If you're in a car and you're in a car accident, you're going to be brought to rest. Whether you have an airbag or you use the dash, you're going to be brought to rest. Agreed? You guys understand what I'm saying, right? If we're trying to catch the egg, and you catch the egg by just standing there, letting it hit your hand, or you catch the egg by cupping it, bringing it down a little ways, the egg's still going to be brought to rest, right? In these cases, I'm using very specific cases, but in those cases, the impulse will be the same. The issue is what causes the impulse. You cause an impulse by applying a force over a period of time. You cause an impulse by applying a force It's not impulse that breaks the glass. It's force that breaks the glass. Did everybody understand what I said? This is worth writing down if you didn't understand it. That in the case of these examples that we've used, the boxing punch, the egg toss, the dropping the glass, the car accident, force causes injury, not impulse. Force changes objects, can break them, crush them. If you want to reduce the force, you have to increase the time. That's what you have to do. If you want to reduce the force, you have to increase the time. That's what cars have been doing for years. So how many of you wear your seatbelt every time you get in the car? All right, so now you've got the lap belt. Have you ever pulled on a seatbelt? Is it stretched very much? You know, a seatbelt can stretch up to 3 inches in a car accident. Think about that. Stretch that much. In a car accident that's severe enough, you have to have your seatbelt replaced because it's been stretched. But the point is, it doesn't feel very stretchy. But it is the first thing to stop you now, is your seatbelt, and then the airbag. In these situations, we keep increasing how long it takes for you to stop by adding these measures in place to start the stopping process sooner. Now, most of your stopping, we have the car do it. So the car starts the stopping process first by it starting to compress while you're still moving forwards. So the front of the car stops because the accident has started, and the internal carriage of the car where you're sitting keeps moving forward as the car is compressing. It's the first part. Then the airbag comes out, starts stopping you personally relative to the car. Then, after you've moved a little bit, the seatbelt takes over. Hopefully, you never touch anything else again. You're trying not to come into contact with the steering wheel or not to come into contact with the dash. In the back of the car, they're trying not to come into contact with the seat in front of them, although generally that's padded now. They hadn't always been. In all of these cases, we're trying to increase the time in order to decrease the force. It's baseball season. I know because I've been signing forms. And because it's baseball season, it's worth noting that One of the things a baseball player wants desperately to do when they come up to bat is to cause a change in momentum of the ball, right? That's the whole point. Now, the easiest way to cheat and do this is to remember that we want a change in momentum of the ball. Pitchers are throwing as fast as they've ever thrown. They're going to throw a 100-mile-an-hour fastball. It's the way it is. What you want to do is turn that ball around right back at them. Maybe a slightly higher elevation, get it over the fence. Your options are to apply a force and time. Roiding up increased the force, right? It increased how hard they could swing the bat. Now, if I can't increase the force anymore, and I want to change the momentum of the ball, the only thing I have to do, or the only thing I have left to manipulate, is time. Well, one way to do that is to recognize that all baseball bats are made from the same kind of hardwood on the level of the playing field, so everybody's using the same bat. And yeah, there's slight variations in mass, but they want everybody to use the same kind of wood, because if they're using the same kind of wood, then the squishiness of the bat is the same for everybody. So if I take a bat in the dark of night and cut off the cap, hollow the inside out, and fill it with something softer, like cork, and then carefully glue the cap back on so the wood grain matches and shave it all off really careful, I could make my bat softer. You've heard of corking the bat. Now the bat needs to have the same mass, so you put like a steel rod in the center of it. So the mass stays the same because cork is a little bit different density than the wood before. And then make sure the balance point is the same because they used to test bats based on the balance point, and I've corked the bat. The ball might be in contact with the bat for maybe 50% longer. 50% is a long time, isn't it? 50% more time means 50% more impulse, which means 50% more change in momentum. I can increase the change in momentum. I didn't swing the bat any harder. I just made the bat squishier. We follow that a little bit? Now, the baseball league did something else. If you don't know, a baseball starts with a rubber core, and then it's wrapped in string on the outside, and then there's a leather hide over the top of that. If you want to manipulate how long the ball is in contact with the bat without cheating, without changing the bat, you change the ball. So they changed the ratio of the size of the rubber core inside the ball to how much string is on the outside of the ball. Ball still weighed the same amount, put the same kind of cowhide on the outside of it, but now the ball stays in contact with the bat for a little bit longer. What did it do? Started hitting more home runs again. Game got more exciting. And what else did we do? We took down how long the pitcher has to throw this stupid ball. Get that ball moving faster so there's more chances for the players to get on base and hit the ball. But hitting the ball changed. Baseball's manipulated the ball tons of times. So is golf. So is every sport that's trying to make a profit. It's only a fun game if people watch, and the way to make people watch is to make the game exciting. How do you make the game exciting? Make hitting the ball more exciting. That's how you do it. Get the ball in play. So don't think for a moment that I'm trying to be negative about sports. I'm not. We want sports to be fun, and we want it to be exciting. But we also probably don't want to be poisoning the players. So make the players healthy, find a way to make the game fun, or at least exciting to watch. So all of these, though, come right back down to this. Right back down to that. Impulse is how you change something's momentum. And momentum is an object's inertia while moving. If you want to change something, you have to apply a force. And how much you can make of a change depends on how long you can apply that force. That's the whole point of impulse. Questions? Pretty straightforward? All right, you know we're going to have to put numbers to this, right? So the first thing I want to do is notes. And we don't have time for a whole lot of numbers, but there's something about this that you really need to have done at least once. So I'm going to give you an example, and I want you to use a calculator. I'm going to take a tennis ball, which is 0.25 kilograms. I'm going to throw it at a wall at a speed of 3 meters per second. Tennis ball strikes the wall, bounces off the wall, and recoils at 2 meters per second. Can you tell me the change in momentum of the ball? Can you tell me the impulse the ball experienced? I'm telling you to be careful because I'm afraid you're going to make a mistake because you didn't hear all the words I said. So I'll even help you. Impulse will be the change in momentum, which will be mv final minus mv initial. Take a minute. I need you to have made this. Before I reveal the answer, did you take into account the direction? Did you notice the ball changed direction? And did you decide on what direction is positive before you started? If you didn't, your answer is probably wrong. For example, if I make this way the positive direction, then my final momentum would be 0.25 times negative 2 minus 0.25 times positive 3. Did you take into account direction? You see, momentum is very much rooted in direction. It's one of the most important parts about momentum. All right.